Well, I've got roughly an hour before I have to do something else, so let's see how much of Section 8 I can cover in that time. We start out by elaborating some on the idea of torque. Back in Section 7, I said that torque is to rotational motion what force is to translational motion. If you've got a soccer ball that's, get myself on camera here. Aim the camera a little bit higher. Okay, so if you've got a soccer ball that's sitting here and you want it to be over there, you apply a force to it. Okay, you kick it and the force causes it to accelerate. If you've got a soccer ball sitting here and you want it to start spinning, you apply a torque to it. Okay, a torque is a twist, a force is a push or a pull. And I talked about how the force, or the force times the lever arm is what equals the torque. But there were a few details I didn't get into. The radius, you know, r sine theta times f. The radius and the force are both vectors. And how to multiply a vector times another vector, well, I'd started talking about that in Section 5 when I introduced the dot product. Torque is a cross product. So that's the first thing to introduce here. So same picture I started out with when I started talking about the dot product back in Section 5. You've got two vectors. In this case, they're going to be a radius vector and a force vector, although the cross product comes up in a number of other situations, especially once we get into the second semester when we're doing magnetism. There's a number of things that are cross products. But whatever these two vectors are, vector A points this way, vector B points this way. If you stick them together so that it makes an angle, they create this angle theta. Dot product, remember, produces a scalar. A vector times a vector just gives you a number. Cross product gives you another vector. Vector times a vector gives you another vector. The dot product, if you calculate it from the magnitudes and the angle anyhow, the dot product was the magnitude of the one vector times the magnitude of the other vector times the cosine of that angle theta. Well, the cross product starts out the same way. Magnitude of the one vector times the magnitude of the other vector times, this time it's going to be the sine instead of the cosine. Not that much of a difference. The main difference is the thing I'm going to stick on the end. A unit vector to give it a direction. N for normal, because the cross product is perpendicular to both of the vectors being multiplied. I'll get that written down and then kind of elaborate. So N for normal. it's a unit vector normal to both A and B. So unit normal vector, a unit vector perpendicular to both A and B. Now, what I've said so far doesn't quite completely pin down the direction. Just saying it's perpendicular to both of these, there's two possible directions that fit that description. It might point out of the blackboard toward you like that, or it might point through the wall toward whoever's on the other side of the wall over there, okay? To choose between these two alternatives, and there's a little sketch drawn on the handout, and also, maybe more importantly, on the formula sheet, but there's this thing called the right-hand rule. The right-hand rule to choose between those two alternatives. And there's different variations on how the right-hand rule gets explained, but it usually goes something like this. If you take your right hand, that's why they call it the right-hand rule, wrap your finger, both these, you think of both vectors as sticking out of the origin, okay? Wrap your fingers around the origin, pointing from the first vector toward the second one. The order matters, okay? Unlike scalar multiplication, and unlike the dot product, the cross product is not commutative. A cross B does not equal B cross A. A cross B is equal to the negative of B cross A, okay? So the order matters. You point your fingers from the first vector toward the second one, your thumb will point in the direction of their product. So A cross B points out of the blackboard this way, whereas B cross A points away from you. And that's kind of what I tried to illustrate with this picture over here on the handout. Wrap your fingers around the vertex of the angle, pointing from the first vector toward the second one, thumb point right. I already said all of that. So let's go back over to the chalkboard. From section 7. If you dig back through your notes from a few days ago, you should find probably more than one place in there where it says that the torque equals this. Now this would be just the magnitude of the torque. I haven't put any little arrows over anything yet. The direction of the torque vector turns out to be, just like I said up here, it's perpendicular to both the radius and force vectors. Or to put it another way, it points along the axis of rotation. Okay, let me move you again. So we have over here the door to the room. Just a second. Turn the monitor so I can see what I'm actually recording here. If I decide to, hopefully you can hear me from over here. If I decide to push the door shut like that, the torque vector points, picture a big long arrow that goes up through the hinges, okay? If I'm pulling the door open, the torque vector points downward. If I'm shutting the door, the torque vector points up through the hinges. The radius vector from the hinges out to where I'm pushing on the door, the radius vector is like that, horizontal, and the force vector is, pushing against the door, also horizontal. The product of those two horizontal vectors is vertical. Sort of a variation on the right-hand rule. Another way you can look at something like this is imagine that you're wrapping your fingers around the axis of rotation, except if you tried to do that, the door and the wall would get in the way. But if you, probably closer to the hammer, camera's a better idea. If you're shutting the door, okay, then the door is turning in that direction. The torque vector points up through the hinges. If you're opening the door, then the door is rotating in this direction, and you're creating a torque that points down through the hinges, okay? So in that way, you have this, this vector that includes both how big the torque is and not only which way you're making the thing rotate, but what the axis of rotation is. Now, for purposes of this course, we are maybe not quite always, but usually going to stick to problems in a plane. About there's good. So, if you've got, for example, this book, as long as we're sticking to problems in a plane, there are only two possible directions it can rotate. Counterclockwise, which according to the right-hand rule is positive, and clockwise, which according to the right-hand rule is a vector pointing along the negative z-axis, okay? But if you get past an introductory course and start talking about how the world works in general, you could, for example, rotate the book this way, or you could rotate the book this way, or any other sort of an axis somewhere in between. So the direction of the torque vector defines what axis you're trying to rotate the thing about, and whether you're trying to turn it the one way or the other around that axis, depending on whether, it points the one way or the other way. So that's kind of the idea behind it. So I guess I was back over here someplace, actually. Hadn't quite finished what I got a half-baked thought written here. Torque is RF sine of theta, where if I make a little sketch, you've got something pivoted about that point, whether it's a wrench that you're spinning around a bolt that's located here, or if it's a drawbridge on some old castle that when the barbarians attacked, you make the drawbridge go up like that. Whatever this thing is, it rotates around that point there. There is some force. Acting at some angle relative to this lever. Theta could be anywhere from 0 to 180 degrees. And the radius vector points from the pivot to the point where the force acts. Okay, so you got a force vector that says how hard you're pulling on the lever and in what direction. And you got a radius vector that defines where that force is acting. And this thing that I wrote a week ago says you've got the magnitude of the one vector times the magnitude of the other vector times the sine of the angle in between, which is exactly how the cross product's magnitude is defined. And for its direction, the torque is in fact along the axis right-handed, like I was just explaining. So the direction is along the axis, right-handed. And so when you condense all that down into a nice, concise notation, it looks like this. Torque is equal to R cross F. Actually, the right-hand rule is something I use fairly often, just tinkering around the house. Like if you're trying to spin a bolt out of, a car engine or whatever, I mean, there's that old thing about righty-tighty, lefty-loosey, but that's not that helpful if you're like under the car looking at the bolt from some angle off to the side instead of looking at it right straight on. And so the thing to keep in mind is that if it's a regular, if it's a right-handed fastener, which 99.99% of threaded fasteners are, every once in a while you find a left-handed bolt on some strange place, and then you use your left hand instead of your right hand. But assuming it's a right-handed fastener, whether it's a bolt or a nut or a screw or whatever, if you want the thing to advance that way, make it turn this way, okay? So you turn it that way and it'll go this way, you turn it the other way and it'll go that way. So one way you hear the right-hand rule explained sometimes is if you imagine turning vector A toward vector B, the cross product points in the direction that a right-handed fastener would advance, except I don't think of it that way. I do it the other way around. I use the right-hand rule to figure out which way the fastener is going to go. Anyhow, time for some illustrations. So a seesaw, like used to be found on many playgrounds. Well, for those of you who may never have seen one of these things, it's just a board mounted on top of some sort of a pivot, and kids used to get on each end and sort of ride back and forth. And let's say you lift up on the end, and there's the radius vector from the pivot to the point where the force is acting. Well, to make it match the way I drew this over here, you really kind of want them with their tails together. So make use of that parallel displacement property that vectors have. Take the force and kind of slide it back over here, either that or take the radius vector and slide it over. One way or another, if you draw them with their tails together, head to tail is for addition. We're talking about multiplication now. Draw them with their tails together so that it forms an angle like that. and then do the right-hand rule the way I was talking about it. First of all, the right-hand rule is only for choosing between two alternatives, okay? Before you do anything with your right hand, you should realize that the torque is going to point, assuming the blackboard is the XY plane, the torque is going to point in the plus Z direction or the minus Z direction. The right-hand rule is just for choosing between those two alternatives. So wrap your fingers around the Z-axis, or wrap them around the vertex of the angle, whichever way you want to think of it, pointing from R toward F. And the thing points this way. You have a torque out of the board. In other words, in this particular case, this unit vector that I was sort of trying to talk about generically over here, so I just called it N. In this particular case, that unit normal vector would be plus K. Okay? It would be pointing in the positive Z direction. And if you'd rather look at it this way, pulling up on it is going to make the seesaw rotate this way. And if you wrap your fingers around the axis, pointing in the direction that you're trying to make it rotate, your thumb points in the plus K direction. So as I said, there's different variations on this, different ways you can look at it. On the other hand, if you lift up on the other end, well, not too surprisingly, reversing the direction of R is going to reverse the direction of the torque. Now you've got a radius vector that points that way. Force still points up. Wrap your fingers around the Z-axis, pointing from R toward F. Thumb points, remember to use your right hand, thumb points into the board. So in that case, this unit vector would be minus K rather than plus K. Time to point this at the handout again for a moment. Maybe I can get that to sharpen up. We'll do this old trick again. Focus on the sheet of paper. Come on. Nope, camera is not in a good mood this morning. Well, oh, there, wait. Yeah, it's a little on the fuzzy side, but you can read it. So this up here is, I already said that, R cross F, the directions along the axis of rotation, right-handed, da-da-da-da, da-da-da-da. Okay, so we're down to this, this example here. Number one. When I was a child, we had these things called toys. Now you go, well, actually I haven't been in a toy store in years, but the last time I did, about half of it was action figures and the other half was some sort of electronic games. And, many years ago, you could get all kinds of stuff. One example of which is this device called a top. What you did is you wound a string around it and then you pulled on the string, which made the top spin around for a few moments, and then it fell over. This is probably why electronic games were invented, actually. But if you can imagine such a thing, you're looking down on it from above here. You've got this round object down on the, where it touches the floor, it would, would come down to a point and kind of pivot there. But there's a string wound around it. You're pulling on it to make it go faster and faster. And the string is unwinding from a radius of 5 centimeters. Anyhow, it doesn't say find the magnitude of the torque. It says find the torque, which would include its direction. So as an example of all of this stuff that I've just been talking about, torque. Now, torque is R cross F, but using the definition of the cross product, that's the magnitude of R times the magnitude of F times the sine of the angle in between times a unit vector to give it a direction. Maybe a little footnote I could slip in is if you think back to section 7, you might remember that this factor here, r sine theta, is something called the lever arm or the moment arm for the force, the perpendicular distance from the axis of rotation to the, anyhow, that's just a little comment in passing. To actually get the answer to the question, all we have to do is throw numbers into this and then attach the correct unit vector. So now there's nothing really wrong with a torque in Newton centimeters, but let's go for preferred SI units and convert to meters. So the radius from the axis of rotation out to where the force acts would be the same as the radius of the top, the 5 centimeters. Theta is the angle that the two vectors make. If you've got, let's see, I got a little space here. If you imagine pulling on the, if the thing was oriented like this, again, looking down from above, this is the top, here's where you're pulling the string. And I think there's one of the problems in the homework. I kind of threw a little bit of a distractor in there. I said that, I don't know what angle I said this was, like 30 degrees or something. Yeah, that's completely irrelevant information. Theta in this relationship is the angle that these two vectors make with each other. The radius is perpendicular to the force because if you pull that string, it's unwinding along a tangent to the circle. And there's a theorem from geometry that says a radius is perpendicular to a tangent. So 90 degrees. Well, in the version with the question there in the handout, I've got the string horizontal anyhow, but if it wasn't, doesn't matter. You're pulling the string with a force of 10 newtons, and right-hand rule. If you pull that string in that direction, it's going to make the top spin counterclockwise. So if you're making the thing rotate that way, the way my fingers are pointed, the direction of the torque vector is, from this camera angle, it's a rather enormous looking thumb, but the point is that it's perpendicular to the page sticking out, okay? Or you could just stick with the counterclockwise is positive, clockwise is negative thing. Positive Z direction, negative Z direction. Anyhow, one way or another, that unit normal vector is k. And you multiply it all together. Well, the next thing it says in the note packet there is example of the vector nature of torque, precession of a gyroscope. The gyroscope being almost the same thing as the top I was just talking about. If you just simply sit that on top of its little stand and let go of it, it falls over. Probably not too much of a surprise there. But if I get it spinning around real good, which is not quite grammatical, don't tell the English department I said that. Just a second. Pulling on the wrong end of the string. Here we go. And then I set it up there. Instead of falling over, the axis traces out the surface of a cone. Well, with some wobbles built into it, that's an additional complicating factor. There are a number of places where you come up with this sort of thing. For example, the Earth does that due to a torque that acts on it from the moon, okay? A little more slowly than what you just saw. Once around takes a few seconds for this gyroscope. In the case of the Earth, from there till you get back to the same place again takes about 26,000 years. So today, the Earth's axis is pointed more or less at the star Polaris. I guess it's about 1 degree off actually. But if you go back 13,000 years ago, it was pointed somewhere around Vega. And 13,000 years from now, it'll be pointed somewhere around Vega again, okay? So same sort of precession that we just saw there. Actually, even in historical times, a bunch of astronomical words you may not know, but where the celestial equator crosses the ecliptic has actually shifted over by one constellation compared to, you know, the time of the ancient Greeks, Babylonians and those sorts of people. If you place electrons, of course they spin, you place them in a magnetic field. They experience a torque from that magnetic field, which makes them precess a lot faster than what you just saw. So anyhow, why does it do that? Well, I just brought this up to kind of point out that all this stuff about vectors along the axis of rotation is, well, you know, it's for real. And it's not just the torque vector that points along the axis of rotation. All of these things I've been talking about for the last week or so, theta, omega, alpha, I haven't gotten to it yet, but angular momentum, when we get to that one in about another week, they all point along the axis of rotation in a right-handed sense. They're all vectors. So what's going on with the gyroscope? Well, here it is. That's looking at it, you know, like this from the side. I didn't bother to draw the little cage that's around it, just the spinny part. So it's on its little stand and it's spinning around, and omega is its angular velocity vector. I'm assuming here that it's spinning, that this side is moving out of the blackboard and this side is moving into it. If it's going around that way, the omega vector points up the axis. If it's rotating the other way, it would point down. Draw a separate picture for this, I think. So just to draw some more vectors on here and not clutter up that picture too much. There's probably not leaning over quite that far. I know it's almost the same, whatever. So once again, this is the wheel that's spinning around, and this is the shaft that it's mounted on. And the center of gravity is probably located somewhere around there, give or take. So the gyroscope's weight, mg, can be thought of as acting at that point. And that's the radius vector from where it's supported here, the point that it kind of pivots around as it precesses. The radius vector from there to there is that. And so if you do the right-hand rule, if you've got a radius vector that points that way and a force vector that points that way, rotate your fingers for a minute. Well, just let's say make a point from R toward F. The right-hand rule says the torque vector points into the blackboard. So based on the right-hand rule, torque vector points that way, perpendicular to the page that we're looking at. Now, consider torque equals I times alpha. Torque equals I times the angular acceleration, where the angular acceleration is the change in omega over the change in time. The moment of inertia and the time are scalars. So d omega has the same direction as the torque vector. The change has the same direction as the torque vector. So if this thing is not spinning, it doesn't all an omega vector. And when you let go of it, it will start to get one as it falls over. D omega would be omega final minus omega initial, and omega initial would be 0. So after a short time, omega final would point in that direction, saying that the gyroscope is rotating about that axis, which is to say, when I let go of it, it falls over if it's not spinning. But if it's already spinning, then it already has an angular velocity around this other axis. And if this is omega initial, and d omega points that way. If it's right directly across omega initial, omega final is going to be the same length, okay? To make the angular velocity vector get longer, you need its change to be that way. To make it get shorter, you need its change to be that way. If d omega is across the vector, that doesn't make it get longer or shorter. It just pushes it over so it points in a different direction. And of course, omega points along the axis of rotation. So the shaft that the wheel is mounted on doesn't tip over, rather it moves into the page, okay? The bottom stays right there, the top moves into the page, and as time passes, you know, it'll continue to get pushed around by this torque that acts on it. So if d omega points into the page, so the tip of this omega vector moves that way rather than getting lengthened or shortened. And so the axis traces a cone instead of falling over. It's kind of like centripetal acceleration. When we were talking about translational motion in, I guess it was section 4, a force across the velocity vector changes its direction. Okay, if you're riding in a car, a force toward the front makes your velocity vector get longer. You go from 50 to 60 miles an hour. A force toward the back makes your velocity vector get shorter. You go from 50 to 40 miles an hour. A force to the side neither speeds up nor slows down the car. Rather, it changes the direction of your velocity vector, makes you follow the curve. This is the rotational version of the same sort of thing. A torque vector that points along the omega vector will make it get longer if it's this way. It'll make it get shorter if it points toward the back of the omega vector. But if it's across it, it doesn't make omega get longer or shorter. So the top doesn't spin faster or slower. Rather, it changes the direction of the angular velocity vector, which means that the axis of rotation gets shifted over. Okay, so that was just to kind of point out that all of this stuff about vectors along the axis of rotation, it's all for real, but for the most part, having raised your awareness about such things, we'll stick pretty much to problems that lie in a plane where there's only clockwise versus counterclockwise to worry about. So I wonder how much more of this I can get through in about 8 or 10 minutes. I don't want to have to break off right in the middle of when I'm saying something. Well, what comes next is a bunch of examples. All this stuff about torque and related topics does seem to be fairly troublesome. So I've gotten in the habit of spending a little class time making you think about it. So I've got this conceptual question here, and actually there's another one further down. What I usually do is kind of pause at this point and say to the class, I want you to try and figure this out on your own. And then I stand there for 3 or 4 minutes. Well, this is a recording, so I can just tell you to pause it. But as I've said many times before, it's the struggle that makes you stronger. So I strongly recommend that you do not just allow the tape to continue playing, except it's not a tape, it's all digitally recorded, but that you do pause it and see if you can figure it out for yourself. Most of the things I know, I learned from doing them wrong. So presumably you are now unpausing the recording. You've got like the hatch on the back of an SUV or minivan or something like that. Does the torque increase, decrease, or stay the same? As it goes up, the torque increases. And here's the explanation. Yeah, it looks a little better, doesn't it? Should have done that when I first came in the room. Here's the hatch on this vehicle. It's pivoted up near the top. There's some kind of a hinge there. And they're usually shaped something sort of like that. But the center of gravity is located, well, maybe not at the exact center, but somewhere near the center anyhow. And so that is the line of action for that force, whose magnitude is mg. That perpendicular to the line of action is the moment arm for that force. And the thing to notice is that when the hatch is closed, the center of gravity is maybe not exactly, but it's pretty close to being right underneath the hinge. So the lever arm is going to be very short. As the hatch comes up, the center of gravity moves over that way, making the lever arm get longer. Since the torque is the force times the moment arm, since the moment arm increases, that means that as you open this thing, the torque will be increasing. And I think I'm going to leave off right there. I'll get back to example, 8-2B at the beginning of the second recording.